Have you ever wondered why even the most powerful classical computers struggle with certain complex problems? It's a question that has puzzled many a mind. The answer lies in the limitations of classical computing. Classical computers operate on a binary system, a fundamental language composed of ones and zeros, referred to as bits. Every piece of data, every command, every image, and every sound is ultimately converted into this binary language for the computer to process. Think of it as a light switch. Either it's on or it's off. These bits can exist in one state at a time, either a 1 or a 0. While this system has worked well for decades, it has inherent limitations when it comes to the amount of data that can be processed simultaneously. Imagine trying to read an entire book by only being able to see one word at a time. It's not impossible, but it would be a slow and tedious process. Similarly, classical computers can only process one configuration of bits at a time, which can be quite restricting when dealing with large-scale computations or complex problems. Consider, for instance, the challenge of factoring large numbers. As the numbers get bigger, the computational power required to factor them increases exponentially. It's like trying to find a needle in a cosmic haystack. Classical computers simply don't have the capacity to handle such tasks efficiently. Or take the simulation of quantum systems. These systems can exist in multiple states at once, a concept that is inherently at odds with the binary nature of classical computing. Simulating such systems requires a level of computational power that is beyond what classical computers can provide. These are just a couple of examples, but they illustrate a fundamental issue. Classical computers, as powerful as they may be, are confined by the boundaries of their binary system. They are forced to tackle complex problems one bit at a time, which can be like trying to empty an ocean with a teaspoon. These are the hurdles that quantum computing aims to overcome. Quantum computing, a term that might sound intimidating, can be simplified to something quite understandable. Picture a traditional computer as a diligent worker, processing tasks one after the other. Now, imagine if this worker could do all these tasks at the same time. That's the magic of quantum computing. At the heart of quantum computing lies the concept of qubits or quantum bits. Unlike the bits in classical computers, which can either be 0 or 1, a qubit can exist in multiple states at once. This is due to a principle known as superposition. Essentially, a qubit is like a coin spinning in the air. It's neither heads nor tails, but a combination of both until it lands. This ability to exist in multiple states at once allows quantum computers to process large amounts of data simultaneously. To understand this, let's consider a simple example. If you had 4 classical bits, they could represent one of 16 possible outcomes. But they could only process one of these outcomes at a time. Now, if you had 4 qubits, they could represent and process all 16 outcomes at the same time. Another fascinating principle of quantum computing is entanglement. When 2 qubits become entangled, the state of one qubit is directly related to the state of the other, no matter how far apart they are. This means that a change in one qubit instantly results in a change in the other. Imagine if you had 2 entangled coins, and no matter where they are, if one lands on heads, the other will land on tails. That's quantum entanglement. Harnessing this power of superposition and entanglement, quantum computers can solve complex problems that would take classical computers an astronomical amount of time. They are like a super-powered multitasker in the world of technology, capable of processing vast amounts of data simultaneously and solving intricate problems with ease. In essence, quantum computing is like having a super-powered multitasker in the world of technology. So, what does this mean for the future of computing? Quantum computing holds a promise of a revolutionary future, a future where we can solve complex problems that are currently out of reach for classical computers. Imagine the possibilities. In the field of cryptography, quantum computers could break codes in a fraction of the time it would take even the most powerful classical computers. This could reshape our online security systems entirely. In drug discovery, quantum computers could simulate the behavior of molecules and proteins, helping scientists design new drugs and therapies with unprecedented precision and speed. And let's not forget climate modeling. Quantum computers could provide us with highly accurate models of our Earth's climate, enabling us to predict and plan for climate change more effectively. Quantum computing promises a future where no problem is too complex to solve, a future where the impossible becomes possible.